Hello there, Mr. Sutton here with this 7.2 lesson supplement. This is the origin story of the Taylor polynomial nth term formula that we saw in this lesson. Because you're not satisfied with just seeing the formula and using it, you want to know where it came from. Well, here we go. To start off this origin story, let's say we're being asked to construct some polynomial with some unknown coefficients, but we're going x squared, x cubed, so typical polynomial. But we want to construct this with the following information at x equals 0. So we know the value of the polynomial should be 5 at the x value 0. Its first derivative there should be 7, second derivative 11, third derivative 13. So we've got all this information. How do we use this to make a polynomial that has these properties of derivatives? So first thing we're going to do is let me just actually plug 0 into my polynomial expression up here. If I actually plug 0 into the original polynomial with these unknown a sub whatever coefficients, anything with an x is going to get zeroed out. So p of 0 is just going to have a value of a sub 0. But now p of 0, they told us right away, should have a value of 5. So that means that p of 0, which is just a sub 0, must have a value of 5. Which means that when I go back and actually write out this polynomial, the very first thing I can write is p of x equals 5. But now we also need the property for this thing that the first derivative, p prime of 0, equals 7. So to figure out what I need to do in terms of a values to make that happen, I'm going to go ahead and just take the derivative of this polynomial expression up here. When I do that, my a sub 0, which is a constant, gets differentiated away. That goes to 0. But now this next one is going to have a value of a sub 1. But then after that, we also have 2 a sub 2x and 3 a sub 3x squared. We're just using our power rule here. But I want to figure out again what a value I need to get a first derivative of 0 when I plug in, or first derivative of 7 when I plug in 0. If I actually plug 0 into p prime, well, these two terms that have x's in them are going away, and I really just have p prime of 0 equals a1. But hold everything, they told us p prime of 0 has a value of 7. So that means a1 has a value of 7. Now, a1 was the coefficient of x in our polynomial. So down here, next to the 5, I can now write a plus 7x. Great. Let's keep going, because my polynomial also needs to have a second derivative of 11 when x is 0. So to figure out what I need to do to make that happen, let me take the derivative of p prime to get p double prime. So p prime of x, this a1 is now a constant that's going away. Over here, we're going to just have 2 a sub 2, and then this is going to be, using my power rule, 6 a sub 3x. Well, the pattern's kind of the same here. Let's plug 0 into this thing now to see what it looks like algebraically. If I plug 0 into p double prime, I've just got 2 a sub 2 because this x term is going away. Now they also told us p double prime of 0 has a value of 11. So let me just set this expression now equal to 11 because that's what it needs to equal. So we see here then that a sub 2 does not equal 11. It equals 11 over 2. There's a little more algebra to do at this point. But now that I've got a sub 2, I can go ahead and plug that in up here, and I can just tack on another term to my polynomial. Now I've got plus 11 over 2 x squared. And then let me go one more because I need my third derivative at 0 to be 13. So let me take one more derivative to get p triple prime. P triple prime of x in general is just going to be 6 a sub 3. This constant of 2 a sub 2 goes away. And again, they told us, well, we need p double prime of 0. So if I plug 0 in here, I actually still have 6 a sub 3, right? Because there's no more x's to get rid of. So this is p triple prime of 0. Now they told us that needs to have a value of 13. So let me set this equal to 13. Doing a little algebra, we see that a sub 3 is going to be 13 over 6. Which means I can complete my polynomial and get plus 13 over 6 x cubed. We're going to do that whole process again one more time, but we're going to do a little more abstractly this time, see if we can find a pattern and find a shortcut. So we're again constructing this polynomial. a sub 0, a sub 1x, a sub 2x squared, and so on and so forth. But now I'm going to throw in a general term, a sub n, x to the n, and that's where we try to get kind of our pattern figured out so we can do this for as many terms as we want. And this time, instead of having my value of my function and its derivatives equaling specific numbers, I'm going to have them match up with the value, first derivative, second derivative, nth derivative of some other function. So if I write it a little more abstractly like this, as long as I can calculate the value and the derivatives of some function, I can use my process to build a polynomial for any function, not just one where there's like specific constant values for these things. So I'm going to start just like I did the last time around by plugging 0 in for p and to see how that relates to this value of f of 0 here. So if I plug 0 into this thing, anything with an x is going away. So p of 0 is just going to be this a sub 0 term here, which means since p of 0 and f of 0 match up, this a sub 0 value is going to be whatever f of 0 is. Again, I didn't give you a specific number, but there's some function where you could presumably figure out what f of 0 was and actually put a number in here. So a sub 0 then is going to be f of 0. That's going to be the first term of your polynomial when you write it out, whatever the function value is at 0. Great. We need the rest of the polynomial, though. So we next have the information that p prime of 0 and f prime of 0 match up. So let me actually take p prime of x for this expression. That's going to get rid of a sub 0 because that was a constant. Next, using our power rule, we've got just 1 times a sub 1, and then 2 a sub 2x, and then 3 a sub 3x squared, and then so on and so forth. I'm not going to bother writing out the general term, but all those terms are there. Now that we've got all this, just like before, we're going to plug in 0 because we need p prime of 0 to tell us something. That's going to get rid of all these x terms, including the ones I didn't bother writing, except for this a sub 1. But now p prime of 0 matches f prime of 0. So a sub 1 apparently has a value of f prime of 0. Now a sub 1 was just the coefficient of x up here. So the next term in my polynomial is just going to be f prime of 0 times x. All right, let me get the next term. So for that, I need to get information about p double prime. P double prime of x, this a sub 1 is going away because it's a constant. And now I'm going to have 2 a sub 2. But I'm going to actually write things out a little bit more, because to get that, I would have to multiply by the current exponent, which is 1. So I could be really just weird and write this as 2 times 1 a sub 2. The reason I'm doing this is I really want you to see where these coefficients are coming from, because that's going to be important for finding a pattern. Next, we can write this as 3 times our exponent of 2 times a sub 3 x to the 1, or just x. And we could keep doing that for all those terms. Now when I plug 0 in for my second derivative, p double prime of 0, that gets rid of all the terms with x's, leaving us with just 2 times 1 a sub 2. But my laziness is kind of taking over at this point. I don't want to keep writing out all these multiplication chains here. I'm just going to write this as 2 factorial a sub 2. But now I see that this has to match f double prime of 0, right? Just like before. So if this is equal to f double prime of 0, that means that a sub 2 really has a value of f double prime of 0 over 2 factorial. Since a sub 2 was the coefficient of x squared, I can now add on the term f double prime of 0 over 2 factorial x squared. And we're almost ready to find a pattern, but let's do one more. Let's get the cubic term here now. For that, I'm going to need to do p triple prime of x. So that's going to get rid of this constant out here with the a sub 2. And next, I'm going to have 3 times 2 times the exponent 1 now. That's the new link in the chain, a sub 3. Plus a whole bunch of terms I'm not going to bother writing out. Plugging in 0 for the third derivative, I see that now 3 factorial a sub 3 is what I get. And based off of this formula here, that's going to match whatever the third derivative at 0 is for the f function, which means a sub 3 really has a value of f triple prime of 0 over 3 factorial. Which means I can now write out the term plus f triple prime of 0 over 3 factorial x cubed. So yeah, there's a pattern here. It's harder to see with these first two terms, but with the last two here, and that's why I did one more term so you could really see this, you have second derivative, second power, second factorial. Then we have third derivative, third power, third factorial. Generalizing this, because it's going to be the same pattern if you keep going here, we're going to have the nth derivative of 0 times, or divided by n factorial times x to the n. That's going to be the general term that you can use to find any term you want of one of these Taylor polynomials. So the nth derivative goes with the nth power, and the nth factorial goes along with them. Now, in case you were always wondering where this n factorial is coming from, that is actually just all those power rules you did to get to the nth derivative. Because the power rule, if you keep using it over and over again, you're multiplying by an exponent that is always going to be 1 less than the exponent that you had before. So this could be 5 times 4 times 3 times 2 times 1 if you wanted the fifth term. It's just power rule in action. So there it is. This is the origin story of your nth term. There you go. Until next time then, this is Mr. Sutton signing off.